Good morning, everyone. I am Ryota Matsui, a master course student at Keio University. I will make a presentation on our paper, Video-Based Hand Tracking for Screening Cervical Myelopathy. First, I want to introduce cervical myelopathy. Spinal cord is a part of the central nervous system which connects brain and body. And spinal cord near the neck is called cervical spinal cord. It is sometimes compressed by some regions, such as degeneration of bones. This pathology is called cervical myelopathy. Cervical myelopathy causes various symptoms, such as upper limb disorders and gait disturbance. In order to screen cervical myelopathy, screening methods which evaluate symptoms are often used. The 10-second grip and release test is a common screening method for it. In this test, patients have repeat gripping and releasing their hand as quickly as possible for 10 seconds. Spine surgeons consider them as a patient if the repetition count is approximately less than 20. We do not require any devices, and we can conduct this test very easily. The simplicity is a big advantage. As it works, many researchers have considered to expand the grip and release test to improve the screening performance. One of the ideas is tracking the grip and release test to screen cervical myelopathy automatically. For example, Watanabe et al. Used a deep motion controller, a non-contact hand tracking device, to track the movement. The data are classified by a random forest classifier. As another approach, Su et al. Used a globe-like sensing device. They classified patients and controls by focusing on fluctuation of sensor values and cycle of the movement. Another tracking method is using a camera. Focusing on other diseases and pathologies, such ideas have already been suggested as related works. For example, Gomez et al. Suggested screening Parkinson's disease, which changes in the ability to move one's face. They use the camera to track their face movement. And the similar approach, Bandini et al. Use a depth camera to screen ALS, which affects facial movements. In this work, we aim to screen cervical myelopathy automatically using a camera. This figure shows the abstract of our method. First, we record the grip and release test with the camera. After the recording, we extract feature values of the hand movement using image processing framework. These values are preprocessed to improve easiness to classify. As the last stage, we use a support vector machine classifier to estimate if they are a cervical myelopathy patient. We think that there are two main contributions. First, we achieve higher screening performance than the conventional method. Second, we use machine learning-based classification model, which does not require spine surgeons to rely on some qualitative indexes. From the next slide, I am going to introduce the detailed method design based on this flowchart. The initial step is recording the grip and release test with the camera. We use the front camera of a smartphone whose frame rate is 30 frames per second. This movie shows the image of the recording. First, Each patient holds their hand just above the smartphone. Then they start the grip and wrist test. During the recording, we pay attention to the hand position, not to move out of the field of view. The recording continues until the following two conditions are met. The repetition count reaches 20 and the recording time exceeds 10 seconds. After the recording, the video is forwarded to a PC for the further processing. As a next step, we track the hand movement with image processing. We use MediaPipe Hands, an image processing framework provided by Google. This video shows the image of hand tracking with MediaPipe. MediaPipe estimates 21 three-dimensional positions shown in this figure and the feature values. Estimating for each frame, these 63 dimensions are described as a time series data. In order to improve data usability, we select two types of adjustment for the feature values. First is to change the coordinate system. That of the raw data is composed of horizontal x, vertical y, and the depth z component. So, if the relative direction between the camera and the hand is not unified, the characteristics of the data should be changed. In order to avoid this change, we rotate the horizontal x and vertical y to x prime and y prime, which are hand-based coordinate system. Second adjustment is to introduce the velocity component. It is calculated by the difference of the positions between the adjacent video frames. With this adjustment, these data increases to 126 dimensions. Before classifying the data, we preprocessed it to improve the easiness to classify. First, we divide the time series data into 20 segments. Since the recording time length is not strictly stabilized, this process means aligning the length of each frame. We set the length of each segment as 64. As frame rate of the videos is 30, the length of each segment is approximately 2 seconds. Since we stabilize both the number of segments and the length of each segment, the adjacent segments may be overlapped if the raw data is short. This figure shows the images of the overlapping. The next stage of preprocessing is fast Fourier transform, converting each of 126 dimensions to frequency components. Considering the mirror frequency components, we choose lower 32 components. As a result, we obtain 4,032 elements for each segment. We can consider that the grip and this movement as a periodic movement. However, the phase characteristics of each segment are not unified. So, selecting only the amplitude component, we can improve the robustness against the phase shift. The last stage of preprocessing is to merge data. If we impose more than one grip and release trial, we merge segments of each trial. But each of 20 segments are distinguished and are not merged. So the merged data also be composed of 20 segments. We use these 20 preprocessed segments as the inputs to the screening classifier. We use a support vector machine classifier to classify each of 20 segments into two classes, cervical myelopathy patient group and control group. As mentioned previously, the data of each participant are composed of 20 segments. Each of them is classified independently each other. So we obtain 20 independent results of the classification. In order to obtain unique classification result, we regard the average of the 20 classifications as the final result. Then I am going to introduce the experiments. In this work, we recorded the grip and release test for 35 experiment participants. They were composed of 20 cervical myelopathy patients and 15 controls, and all of them were right-handed. Each of them was recorded twice, the right hand and the left hand. As a result, we collected 70 videos. The detailed information about the participants is shown in this table. With these videos, we validate performance of our method using tenfold cross-validation. Please note that the split was not video, but participant. So, data of the same participant did not be included in both the training data and the test data. We evaluated our method through 3 evaluation indexes: sensitivity, specificity, and AUC. Sensitivity and specificity indicate the accuracy for patients and controls respectively. However, we can obtain multiple combinations of them depending on the threshold. Log curve shows the relationship between them as a graph, and area under it is called AUC. Maximum AUC is 1, and the higher AUC is, the better the performance of the classification is. First experiment is validation for each feature value. We validate the evaluation indexes for the selected combination of feature values. The objective is to select mainly contributing feature values for the classification. We select 9 combinations. The first 5 ones are 4 points of each finger, and the rest is fingertip and each joint of 5 fingers. As shown in this figure, Mediapipe estimated 4 points for each finger. Types of joints are shown in this figure. These 2 tables show AUC for 9 combinations. We can see that fingers of the thumb side and joint of the wrist side tend to show higher AUC than those of the little finger side and the fingertip side. On the other hand, sensitivity and specificity are stabilized for all combinations. So we think that this difference is relatively small. Following these results, we selected PIP and MCP joints of thumb and index fingers for further validations. As the main validation, we validate with the feature values selected in the previous validation. We conducted it under 3 conditions, use videos of both hands, right hand and left hand. The results are shown in these 3 figures. The first one shows the evaluation indexes, and the other shows log curve for right hand and left hands, respectively. As a best performance, sensitivity, specificity, and AUC using only the right hand were about 0.90, 0.93, and 0.95, respectively. One of the characteristic results is that validation with right hands shows higher performance than that with only left hands. We think that this result is influenced by participants' dominant hands. As mentioned, all of 35 participants were right-handed. We can generally move our dominant hand more easily than the non-dominant hand. This difference may affect the easiness to classify patients and controls. In this paper, we recognize the performance for right hand as a final validation result. We compare the performance of our method with other screening methods for cervical myelopathy, the conventional 10-second grip and release test, and the glove-like device-based method suggested by Su et al. As a result, all of three evaluation indexes, sensitivity, specificity, and AUC for our method is higher than the other methods. So we think that there is potential to be used in actual medical settings as a new screening method for cervical myelopathy. On the other hand, we would like to mention some limitations. First limitation is that our method only focuses on hand disorders, a symptom of cervical myelopathy. Although this is not limited only to our method, we need to diagnose cervical myelopathy by not only our method, but also various symptoms and image inspections. Second limitation is that our method does not currently take other pathologies and diseases into account. So, as a future work, we aim to apply to them, such as carpal tunnel syndrome. It may contribute to not only detection of hand disorders, but also differential diagnosis. And our ultimate goal is to apply to actual medical settings. Our method can be used as an initial screening method used by local doctors and care workers. Connecting these results to further medical services, our method may contribute to the early detection of cervical myelopathy. This is the end of our presentation. Thank you for your listening, and we look forward to your questions.